Today we're going to be looking at permutations and probability. Our objectives are to be able to find the number of ways an event can occur using permutations, permutations with repetition, circular permutations, and to be able to find the probability of an event using permutations. We're first going to start with the fundamental counting principle. And what that says is if one event can occur in m ways and another event can occur in n ways, then the number of ways that both events can occur is equal to m times n. Now you probably did some of this stuff when you were younger, but instead of just doing the multiplication, you might have done like a tree diagram. Your first event has 4 different options, and then the second event has 2 options, and then you wanted to know how many different ways you could do it, and you had to count all the branches, and then you got 8 ways. Well, the easier way is, well, if the first event can happen in 4 ways, the second event has 2 options, we could just do 4 times 2 and get 8. And that's what we're going to use instead of drawing it out. In our first example, it says you go out to dinner and have the choice of 3 salads, 4 soups, 6 entrees, and 4 desserts. A asks, how many different ways can you order if you have 1 salad, 1 soup, 1 entree, and 1 dessert? Well, that's 4 separate events. So I'm going to have 4 things multiplied together instead of 2. So the first one's going to be salads, and there are 3 options for salads, 4 for soup, 6 for my entrees, and 4 for desserts. So if I multiply those 4 numbers together, I'm going to get 288. What that means is that if I go to, say, this restaurant, and each time I order at least one thing different, I can actually go there 288 times in a row, and every single day will be a tiny bit different than the day before. There'll be no repeats. If I go 289 days, I will be forced to repeat. And that's just by multiplying out. As you can see, that would be really hard to do in a tree diagram, and that's why we go to just the multiplication. B says, well, how many different ways can you order if you have 1 salad or soup? And lots of places say soup or salad, not soup and salad. So let's think about this. Now I'm making 3 decisions. I'm deciding what soup or salad do I want, what entree, and what dessert. Well, the entree and the dessert didn't change, but 1 salad or 1 soup. So now I have to choose 1 out of how many? Well, if I look, there are 7 options, so I'm going to put a 7 here. 7 times 6 times 4 is 168. So if I only get 1 soup or salad, I'm only going to have 168 different ways that I can order these 3 items. So now, what is a permutation? A permutation is just the number of ways that n elements can be arranged in order. And again, you're going to see this come up a lot, this n. And this just means we don't know how many there are, but if we want to take n elements and put them in order, we call that a permutation. And to help us out with that, we're going to use something called a factorial. And a factorial is the product of the positive integers from n to 1. So an example would be 5 factorial. We use this little symbol right here, this exclamation point. That is our factorial. So we say this 5 factorial, which means we're going to go from n to 1, and we're going to use positive integers. Remember, integers are, our whole numbers that are, but we're only going to deal with the positive ones. So I have 5 times 4 times 3 times 2 times 1, which gives me a total of 120. We do have a special case, though, of 0 factorial. And if you ever see 0 factorial, that is actually equal to 1. There's one way to do nothing. You don't do it. So let's go through some examples. Answer the following. You have 7 books for school, and how many different ways can you arrange them on a bookshelf? So let's think about this. We have all these different things. We got to make 7 decisions. We're going to decide what book goes first, then what book goes second, and so on. Now, we're going to assume we have 7 books for school. They're hopefully all different books, or else that'd be kind of weird. So we have 7 books for school. So now I want to decide how many options I can do this in. So let's think. If I have... Okay, those are my 7 books. I first have to decide how many options do I have for the first spot. Well, there's 7 books in here, so I have 7 options for the first one. But once I place a book down and I go to the next one, I don't have 7 options anymore. Now I only have 6. And then the next time I only have 5, then 4, then 3, then 2. And then when I get to that last space, there's only 1 book remaining to put in that spot. Now you could write all that out, or if you understand that you're going to be starting with 7 books and you're going to be decreasing by 1 each time, going down all the way to 1, we could write that as 7 factorial. Let me show you how you would type that into your calculator. So if you have your calculator and turn it on, okay, what we're going to do is clear anything that's actually on it. And we're going to type in the number 7, and then to get to the factorial, I'm going to hit the math button right underneath our alpha key, and I'm going to go over the probability. You can go 3 to the right or just hit left once, and then the fourth option is our factorial, our exclamation point. So I'm going to hit enter, and I get 5,040. So again, that means if I have 7 books, and I just want to arrange them on a bookshelf, there would be 5,040 different ways that I can do that. And it doesn't mean that every book's in a different position. It just means that out of all those times, there are no 2 that are identical. Number 2 says, using the letters from the word orange, O-R-A-N-G-E, how many different arrangements can be made if you cannot repeat any of those letters? So it's the same idea. I'd be wanting to make a new word. 1, 2, 3, 4. There's 6 letters, so I'd have to have 6. And again, I have 6 options for the first, then 5, 4, 3, 2, 1. Again, it says you cannot repeat, so I know that I can't use, say, the letter R twice, so it's going to go down by 1. This is the same thing as 6 factorial. And again, if I type that in my calculator, I'm going to get 720. That means there are 720 ways. Picture these being Scrabble tiles, and if you rearrange them, you can come up with 720 different arrangements. 3 is actually a little bit different. It says your van has 6 seats, 2 in the front, 2 in the middle, and 2 in the back. Only Val and Kelly are willing to drive. Damien has to sit in the front due to car sickness, and the other 3 people don't care where they sit. And how many different ways can the seats in the van be filled? Well, I always like to draw it out so it looks like what the problem says. So I have 1, 2 seats in the front, 2 in the middle, 2 in the back. And again, we're just going to be multiplying these numbers together, so it doesn't matter if my dashes are next to each other, in a circle pattern, stacked, it doesn't matter. Everything is going to eventually be multiplied together. So, let's see who we have. We have Val, we have Kelly, we have Damien, and it says 3 other people. I'm just going to write A, B, C, just so we kind of keep track of them. Now it says only Val and Kelly are willing to drive. Okay, so this would be our driver's seat. So how many options do I have? Well, only 2 people are willing to drive. But once one of those people sit down, and again, I don't know if it's Val or Kelly, I'm going to cross one of them off because that person can no longer sit in one of the 5 remaining seats. Then I go to my next constraint, and I always want to start with the constraints they give us. Damien has to sit in the front due to car sickness. So here's the only other seat in the front, and he's not going to drive, so that means Damien has to sit here, so that means I only have one option. Damien has to sit there. So now I have the driver, I have the person who's sitting in front, and it says the other 3 people don't care where they sit. Well, if Val said she would drive, she's either going to drive or sit somewhere else. These 3 people don't care. So now I have 4 seats and 4 people. It doesn't matter where you start. I have 4 options for this seat, then 3, then 2, then 1. Again, it doesn't matter what order because we're just multiplying. This would be the same if I would have done something like this. Okay, it doesn't matter. These could be in a completely different order. It all works out. So if I multiply all of this out, I'm going to get a total of 48 different ways that these people can sit in this van. Number 4 says, you are taking a multiple choice test with 10 questions. There are 4 possible answers for each question, A, B, C, and D. And how many different ways can you answer the questions on the test? And we're going to assume that you answer every question, that you can't leave any blank. So let's think about this. If I keep going, there are 10 questions. So if I think about the first question, how many options do I have? I can answer A, B, C, or D, so I have 4 options. If I go to question 2, well, I can answer A, B, C, or D, I have 4. Every single question has 4 options. So if I keep writing this out, I have 4, and it'll happen 10 times because there are 10 questions. So again, this is going to be a pretty large number. So I'm going to do 4 to the 10th power. And then when I write this out, I have 1048576. Okay, so that's 1,048,576 different ways. It's quite a lot. But then it says, what is the probability that you got all of the questions on the test correct? Okay, or questions correct on the test. Probability, and we just spent time doing this, is going to be our fraction answer. And it's how many ways that you want out of the total. Well, if this is the total number of ways you can answer the test, 1,048,576. Of all those tests, how many ways are there to get all the questions right? Well, if you think about it, if I was to have an answer key for this test, how many answer keys would I have? Well, there'd only be one. There's only one way to get the test right. You answer every single question right. So if I want to think about that, if I think about the test, if I want to get the question right, there's only one right answer for the first problem, one right answer for the second, one right answer for the third, and so on. 1 to the 10th power is 1. So if you want to know what's the probability that you just, if you answer a 10-question multiple choice test, what is the probability you get it right? I'm going to do 1 divided by my answer, and I get, now this is in scientific notation, but 0.12345 this would be my 7th number, and so on. That's the probability that I get 100%. Now you know that if you take a 10-question multiple choice test, that someone's going to get it right, and actually everyone could get it 100% if they actually studied. Probability assumes that every answer has the equal likely chance of being picked. Now when you study, some answers don't make sense, so you're going to most likely choose, if you've studied, the correct answer. Okay, so this is if you just blindly guess. That's what all this probability does. Okay, this is truly the number of ways you can answer it, but the chance of you getting 100% is much higher than this if you study. If you just randomly guess and know nothing about the information, this would be the chance that you would get 100%. So what if we have repetition in our problem? So we have a formula for finding the number of permutations if objects repeat. So if the same object comes up more than one time, we actually change our formula. The formula is n factorial divided by the number of repeat factorial. And I'll show you what this means in a couple of examples. So our first example says, in how many different ways can the letters in the word Connecticut be arranged? Now this is different than the word orange, okay, because orange didn't have any repeats. But if we look here, we have some repeated letters. So if I look at the letter C, there's 1, 2, 3 C's. If I look at the letter O, there's only one O, so that one doesn't repeat. The next letter is N. 1, 2, 2 N's. The next letter is an E. There's actually only one E. Then the next letter is a T. There are 1, 2 T's. And then there's a U. Sorry, there's an I and a U. Okay, I believe there's only one I, and there's only one U. Okay, so if we go through this, 3, 4, 5, 6, 7, 8, 9, 10, 11, we have a total of 11 letters. It's important to know two things when you have repetition. How many total letters and which ones repeat. So again, let's make sure 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, so they match up. So we are going to take, it says the n factorial, so there are n letters, so this is going to be 11 factorial, and now we're going to divide by the repeats. So the ones that repeat are the C, the N, and the T. So it repeated 3 times, so I'm going to divide by 3 factorial. The N repeated twice, so 2 factorial. And the T repeated twice, 2 factorial. You cannot combine these. These are not like terms because they're factorials. So you have to leave them separate. Now, many students get this wrong on a quiz and test because they don't know how to correctly type it in their calculator. Whenever you have a fraction, your denominator needs to be in one big parenthesis in order to get it correct. So when I pull up the calculator, okay, I'm going to take 11 factorial, divide it by, and I'm going to use one parenthesis for the entire bottom. Now, I know what these are. So again, to save you some time and make it a little bit easier, 3 factorial means 3 times 2 times 1. Okay, so again, this is 3, 2, 1, which is 6. 2 factorial means 2 times 1, which is 2. So really I'm dividing by 6 times 2 times 2, or dividing by 24. Okay, so you could just type in 11 factorial divided by 24, which is what I would do. However, if you don't know that, this is what it should look like. 3 factorial, it's just tedious to type it in, times 2 factorial times 2 factorial. That is what you could also do, but you just have to make sure that there's one big parenthesis in the denominator, not a bunch of little ones. Okay, so this is going to give me this large answer of 1,000, sorry, what do we have, 1663200. So 1,663,200. That's how many different ways to rearrange these. Now the reason we have to worry about repetition is because, say these were Scrabble tiles. If I was in a room and I put down the word Connecticut, okay, but then you came in and switched these 2 tiles, would it look different? And the answer is no, it would still look like the word Connecticut. So that's why we have to divide and we actually get less answers. If I just type in what is 11, what is 11 factorial? Let's try this one more time. Sorry, 11 factorial. Okay, I'm going to get a much larger answer, but because I have repetition and letters that repeat, I actually get a much smaller answer because rearranging all these letters that are the same doesn't give me a new answer, a new possible arrangement. If these were all different letters, switching these two would be a new option, so that's why the number would get larger. Okay, so let's look at the last example here. There are 13 cages in a row at a pet store. The manager has 3 tabby kittens, 4 calico kittens, 2 German Shepherd puppies, and 4 collie puppies. And how many different ways can he arrange the different types of animals if each one gets their own cage? Now, this one stresses the word types. And the thing is because you might think, well, there is no repetition because even though you have 3 tabby kittens, each kitten is different. You'd be able to tell the difference. Like anyone who has pets, say you have a collie, you would be able to tell your collie different from the one down the street because of their personality and stuff like that. So that's why we're just talking about the types. There is repetition in the type of kitten. So that's why we're going to deal with this same thing as we have letters. And you might think, well, how do I do that when there's not letters to think about repeating? Well, if I have 3 tabby kittens, that's the same as having 3 T's. Think of it that way. If I have 4 calico kittens, or 4 German Shepherd puppies, or collie puppies, I'll just use a P for collie puppy. It is the same as like having letters. If I switch these two, it looks the same. So again, how many total do I have? 3 plus 4 is 7, 8, 9, so I have 13 factorial. And every single one of the types repeat. So I have divide by 3 factorial, 4 factorial, 2 factorial. Oh, sorry, I only had 2 German Shepherd puppies. Not to confuse you there. And then 4 factorial. So again, I'm going to type this in my calculator as 13 factorial divided by 1 big parentheses. I know 3 factorial is 6, so I can just do 6. 4 factorial is 4 times 3 times 2 times 1, which is 24, times 2 factorial is 2. 4 factorial is 4 times 3 times 2 times 1, which again is 24. That's another way you could do it. Save yourself a lot of time. So this answer comes out to be 900,900. That's how many different ways I can rearrange the types of animals at this pet store. So what are the formulas for circular permutations? This is all written out for you on your notes, but when you have things in a circular form, we actually get less options because when it's a circle, there's really no beginning or end. There's no first position, last position. So if you picture having, say, keys on a key ring, if you have all the keys spread out and you turn it, you didn't change anything. It's still the same option even though it looks a little different. Okay, so we have 4 different formulas. We have a circular with no flip allowed, circular with a flip allowed, restrictions on our circle with no flip, and restrictions on our circle with a flip. Now if you look here, whenever a flip is allowed, we're going to divide by 2. And by flip I mean an object that can you actually physically flip upside down. So keys on a key ring, beads around a necklace. If you take a necklace or a bracelet and it's laying on a table, you could flip it upside down. It might look different, but it's really the same arrangement because you haven't changed any of the ordering. Those are the kind of things that we flip. Things with no flip are people seated around a circular table. So if they're seated around a circular table, you're not going to take them and flip them upside down and say, well, now it's different. So when you have a flip allowed, we divide by 2. Okay? Now, when we have something that's circular, okay, we actually don't deal with n factorial. So if I have 11 beads and I want to order them in a row, it would be 11, 10, 9, 8, 7, so it would be 11 factorial. But if they're in a circle, I don't have a beginning and an end. So I actually get one less, so it's not, say, 10 factorial, it would be, say, 9 factorial. It's always n minus 1. And if you ever have any sort of restriction for your circle, so for example, you have a bracelet, but there's a clasp, so you can open it and then there's actually a beginning and an end. Or if you have something in a circle, but there's one thing that's fixed, so it doesn't ever change its position, then we actually don't deal with it as a circular problem. We actually deal with it like we've been dealing with the last problems as a just normal permutation where we either use factorial or our dashed lines to help us out. So we're going to go through 4 examples so we can kind of see the difference between these 4 different formulas. And how many different ways can you arrange the letters of the word math in a circle? So there's 2 questions I have to ask myself. So again, I'm just going to kind of draw this out so you kind of can see it. First of all, I'm going to think of myself, are there any restrictions? Did it say certain letters have to be next to each other? Is one of these letters fixed so I can't move but the other ones can? And the answer to that is no. I'm just putting the letters math in a circle. So this is a true circular problem. Now, if I took this, would I be able to flip these upside down and get the same answer? Well, the answer to that is no. Even though all of these letters are pretty much symmetric, if I took these on a piece of paper and flipped it upside down, it's not like you're like, oh, that looks like a different option. It doesn't make sense to flip this upside down. So this is circular with no flip. So because it's circular, I have 4 objects, M-A-T-H. So I'm going to do 4 minus 1. There's no flip, so I'm not going to divide by 2. So this is the same as 4 minus 1 is 3. 3 factorial. 3 times 2 times 1 is 6. So there are actually 6 ways to rearrange the letters in the word math. Number 2 says at a circular table there are 6 chairs. So 1, 2, 3, 4, 5, 6. It's always nice to have a visual. Mark, Steve, Ed, Georgia, Dale, and Jim are all sitting at the table, but Jim has to sit next to Ed. So now I'm getting some sort of restriction. So this restriction means it's non-circular. So I have a restriction. It's telling me things have to be next to each other, so that makes it more like a linear. And how many ways can this be done? Well, this is also people sitting at a table, and we're not going to be able to flip them upside down and think it's a different option. So this is a restriction with no flip, which really means it's just like a normal line problem. Okay, so I know Jim and Ed have to sit next to each other. So let's pick any 2 chairs and say, well, these are the chairs that Ed and Jim are going to sit into. And again, it's a circular problem, so it really doesn't matter which chairs we pick. So if Ed and Jim have to sit next to each other, I want to pick one chair. I don't know if it's Ed or Jim, so I have 2 options for the first chair. And then once one of them sits down, I only have one for the other. So that's Ed and Jim have sat down. But now I still have Mark, Steve, Georgia, and Dale that need to sit down. So I have 4 people. It doesn't matter. There's no restriction, so I'm just going to pick anywhere to start. I have 4 options for this one. Once someone sits down, I have 3, then 2, then 1. So again, if I go through this and multiply all of those out, I'm going to get 48 possible options. In our third example, it says you have 5 different keys on a key ring. How many different ways can they be placed on the ring? Okay, so I have 5 keys. I have this little key ring. I'm going to have all these different keys on here. Okay, and again, you don't have to draw pictures for it, but I'm just going to do this for here for now, and forgive my ugly looking keys. But those are 5 keys on a key ring. So, again, there's no restriction. It didn't tell me that certain ones had to be next to each other. None of them are fixed in a certain place. So this is a true circular problem. Now, if you have a key ring, if I flip it upside down, that's perfectly acceptable, because it's not like you can't have a key in a flip direction, and if I throw them down on the table and someone picks them up and flips them over, they might look like they're in a different order. So this is circular with a flip. So again, I have 5 keys, so that's n equals 5. Circular tells me I'm not going to do 5 factorial, I'm going to do 5 minus 1 factorial. And because I'm flipping this, we divide by 2, because we actually get half as many options, because I might look like I have a bunch of options, but if I flip it over, it'll actually take account of one of those. And you can look up other videos that talk about circular permutations, which I'm sure they'll have a lot of good visuals of this, and we'll talk about it a little bit in class. So 5 minus 1 is 4. 4 factorial is 24. So this is 24 divided by 2. So if I have 5 keys on a key ring, there are 12 different ways that I can place them on that ring. And our last one here. You have 7 different beads on a bracelet that has a clasp. How many different ways can the beads be placed on the bracelet? So again, we have this bracelet, but there's this little clasp here, and that's not going anywhere. So because I have a clasp, if there's a bead here, okay, it can't just jump to this side. I can scroll it, back and forth, but there's almost like a starting position. This is the first position, and then so on. I can't just keep spinning these round and round. So this is one that has a restriction. Okay. Now, is a bracelet something that if you lay it on a table, you can flip it over and have it look like an acceptable answer? Yes. So this is going to be a restriction with a flip. So again, we have 7 different beads, so my n is 7, and if it has a restriction of 7, okay, it's like having my dash lines. You have 7 options for the first bead, then 6, 5, 4, and so on. So I'm going to write that as 7 factorial. And because I can flip it, I'm going to divide by 2. From earlier, we did 7 factorial is 5,040. If I divide that by 2, I'm going to get 2,520 different options. I hope you feel a little bit better about permutations and some probability. Again, we didn't stress the probability too much here, but it's the whole idea of counting. And if you want to do probability, you take the number of ways of what you want over the total number of ways, just like we did with the multiple choice problem. So we've done permutations, permutations that have repetition in it, and circular permutations.